Okay, any second now.
Got it.
Being streamed.
I think we're ready as we can be. I got a little smoke from that Canadian fire in my living room. My apologies.
Good
My
comeback.
house hasn't burned down. This is Ron Heron and the gang I'll introduce you to in a minute, folks. It's the SBAU Astro Hour. Doggone it, the regular Monday morning vlog podcast. Vlog, means we're sort of on video. Podcast meaning you can hear us. I don't know how many people just listen to this program. It's our longtime South Coast Astronomy and Telescope Club, the Santa Barbara Astronomical Unit, from 10 to 11. No, it isn't. 11 to 12. I'm sorry. Every Monday morning on YouTube, you can see us.
7-Eleven is the name of a store.
What is?
7-Eleven is the name of a store.
Maybe that's what I'm thinking of. I don't know. I got problems, but I'm amazed I'm on here. I really am. SBAU club members can watch. A lot of you astrophysics aficionados who we're going to get in the club sooner or later. And you can go to sbau.org and get all the details as I've been doing lately. Now, let's talk about what we're going to talk about this week. June 19th to the 25th, our 122nd program of the SBAU Astro Hour. Going to put into place in time the positions of our moon. We're getting ready for a big turnover date in I guess, later this week. And one dwarf planet out there in the asteroid belt, plus solstice is coming. That's what I was talking about earlier. And 4 views of one galaxy, one distant one, thanks to gravitational lensing. We're going to talk about that if we get to it this hour and look at the star and the Dipper's handle as a central star in Cygnus, which is, I believe, the Swan. Is that right?
Yep.
Okay. And seeing a super, I had to turn my lamp off and I can't read my writing. A super, what is it that Chuck McPartland always signs off? Asta Nebula? That's what, something like that anyway. That's what it is. And it's in another galaxy. It's not even in ours. And we're going to give you 2 equations, 2 formulas this hour. One of them will probably lose you, but I'm going to hang on and see if I can get through it. And the other, a man named Drake, gave us a very fascinating equation. We're going to talk about the Drake equation, and that we'll be able to understand. Now let's meet the gang. Jerry Wilson, still our president. Hello, Jerry. Thank you for
Good morning.
I'm on because of him and because of Chuck McPartland, our outreach coordinator, who's both married to wives named Pat. Chuck's wife is a merchandise manager. Pat Forgy is Jerry's wife, and she's a very good support lady. And we're all going, I guess, a week from tonight, aren't we, to the big party out there? Haul us home in hefty bags from Jerry's big, 79th trip around the sun? That's the way she put it. Yeah, we have Bruce Murdoch, who's married to Bonnie and runs the Santa Barbara Theater Organ Society. Bruce, good to have you on board. Look nice and warm. And last time I looked, it was sunny outside. I thought it was all over as this June gloom as of Saturday, when my daughter and her husband took me out to an incredible meal at the beach, and the whole damn world was at the beach, including those rockets that go by, those muscle cars trying to impress us. Anyway, let's do some funny stuff. These are Jerry's forwarded weekly silly science cartoons that he saves and throws up and gets us in a good mood. And I always laugh at most of them. Some of them are just intriguing and interesting to look at. Here we go, ladies and gentlemen. They're lined up. Which one is this one? Astrology pushback? Please stop blaming us for your strange behavior.
Yeah.
Astrology. And okay, you're going to have to explain that now.
Oh, this is a pushback for people who believe in astrology. Our fates are not are not daily defined by celestial objects, especially the lineup of the planets. If something big hits us, then our fate is defined by the stars. But other than that, it's not.
Okay. And what's missing in that lineup? Well, never mind. This guy is from the.
It was cut off at the bottom.
Okay. Beings that can't distinguish between entomology and etymology bug me in a way I just can't put into words. That's a scene from The Fly, isn't it?
There could be any movie that.
I had acne like that when I was a kid. Couple of talking cats. Why they make bad scientists? Well, apparently the rat got eaten or escaped. Did you eat the control group? The rats, my God. And yet every one of these guys on the screen have cats, I think,
Yeah.
right? Except me. Ground control, which is what we're looking at to Major Tom.
Yep. And that's the only 4 we had last week.
Oh,
There are 2 more you guys got last night and this morning, but I didn't get those in here for that. They'll be next week.
motherly advice from Star Trek. Okay. 4 visions of ZN Zwicky. You remember that one? Who was
Supernova's
ZN
wikis.
Fritz
SS.
Zwicky?
Yeah, there was something about a Zwicky. I've heard the name before. I'm not sure.
Well,
He was an-
Fritz
he was an
Zwicky,
astronomer.
Fritz Zwicky was a Swiss astronomer working in the US. He's the one that was one of the first to detect dark matter. And this supernova was found by a telescope, a robotic telescope that's named after him called the Zwicky Transient Factory.
Oh, okay. I've got that in my comedy corner. I'm sorry. That's part of the talking points. We're going to look at the new moon coming. Is this how it looks?
No, new moon passed. This is the about a 1.5 day old moon. So this is what it'll look like this evening, June 19th. This is 4 in the afternoon, but it won't look significantly different in the early evening. This will be at a 1.5 day old moon. This is a very difficult moon to spot in the sky. It's very slight. You need clear skies and a good horizon. There used to be a contest I've seen that pops up every now and then of who can get the earliest moon. And I think this is about the record, about 1.5 days.
All those Maris.
Yeah.
That are in the dark.
So we still have most of the night as really dark, not polluted by moonlight. So you can see faint fuzzies and take photos if you're inclined.
Can you
And
see?
the
The
planet-
last 2 nights have been pretty good, except after about midnight or thereabouts, the clouds came in again.
Oh, my nights, hopefully tonight's different, but the clouds are in all day and all night here.
Oh, really? Okay, well, here the clouds are in all day, but after the sun went down, the sky is
Oh.
clear.
Well, after the sun went down, I'm usually previously occupied, and so I haven't gone outside to look, but maybe it did.
Yeah, we had a good
But
night. at the
tonight, I'm
studio.
hopeful. It looks very clear this morning.
Now
was-
joining us is Tom Whittemore, our
Yeah.
editor of the newsletter. Tom, I hope you can hear us and we can hear you. You can join
He's
us.
muted right now.
Okay.
Yeah, you're muted. I muted you. There was background noise in there.
Had to go check the bread in the oven. No,
Yeah.
no, you're not.
Well, I'm sorry I missed last night, but it was Father's Day. The Sunday was Father's Day, but my daughter came up on Saturday and, brought us a nice dinner. So
Okay.
that occupied my evening.
So
Well,
instead of list the positions of the planets, I just show them in the chart,
Right.
3 charts to get.
And last night, Jerry, they were in full bore here. And you can see Venus and Mars point right to Regulus.
Oh, yeah,
Yeah.
they were great. They were
Yeah.
great.
Yeah, so,
There's
last
Regulus
night I
there,
went
and
out,
there's
we had
Venus and Mars.
actually two clear nights here, Saturday night, Sunday night.
Wow.
And I noticed also about 9 o'clock in the evening that Castor and Pollux were just hanging right over the northwest, right over the horizon.
what did you just say?
Castor and Pollux, the heads of Gemini.
Oh, Castor and Pollux. Yeah.
See right here, Castor and Pollux.
Yeah.
But some of
So-
these can be seen before dawn, others after sunset. And do they set?
No, this is what the sky looks like in the west. They're setting. This is just after sunset. You can see the sun in this planetarium software, how they represent it. The sun is just set here. This is
Right.
8:30 tomorrow night.
Well, that can't be all the visible planets in one picture, can it?
It's all the visible planets at that time.
Yep.
Okay.
There's just,
And Mars is really weak right now. It's just really weak.
yeah, very faint.
It's naked eye visible if you know where to look.
Oh, yeah. No, it's easy to see.
Yeah, Venus is the brightest thing up.
Right to Regulus.
Okay.
And you can, the lion is standing tall when the sun goes down. Yeah, I'm talking around 9 o'clock.
Yeah, that picture was from 8:30.
Mhm.
This is in the morning, and this is 6 a.m.
Mhm.
tomorrow morning. And here you can see the sun is just about to rise.
Mhm.
This has Mercury, Uranus, and Jupiter,
Mhm.
and the Pleiades. And these are in Taurus, now a
Pleiades.
morning constellation.
When we have our second Saturday star parties, what planets do you usually see? I guess Saturn is really up high, isn't it, usually? And what
Yeah.
else?
That depends on what time of year it is. Saturn is in the morning sky now. It's just about to transition past midnight when it rises.
But
And
can we ultimately see all the planets from in the middle of those trees on that walkway outside the observatory at the museum at night straight up? There's trees everywhere around us, you know.
Well, Ron, the ecliptic goes, through our sky. So at some point they're going to be in there, but it's not like
Right.
it happens every night. Sometimes they're too close to the sun from our point of view.
Yeah, and I was gonna mention, Chuck, did you guys get any more people to come to the Westmont?
Yeah, it cleared up nicely. We didn't get any more. We got a whole family of like 11.
Okay,
But that was it. Nobody else came because it didn't clear up till a little after 9.
right. We did get Venus, remember? In
Yeah.
the 8. Yeah.
So you focus the Westmont Observatory telescope on one thing and just leave it there?
No,
No,
you got-
no.
no,
No.
Ken was bouncing around to stuff. He did M13 and he did Venus. And
Mhm.
And it's got the tracking mechanism.
I was doing the supernova and M101.
Oh, did you get it?
Yeah,
Oh,
it's
nice.
still
nice.
quite bright.
Okay.
So
We did
this
that
is
at Refugio also.
Okay.
this is the sky earlier in the morning tomorrow. It's 4 a.m. There's Neptune, Saturn, and Pluto.
Pluto.
So I still give Pluto an honorable mention here. But these are in Aquarius and Capricorn.
Mhm.
So these are still morning objects. It'll be a few more months before we see those in the evening skies.
What if the James Webb can see Pluto pretty much like New Horizons did with that big heart-shaped?
No,
No way.
Oh,
We don't have anything that can resolve surface details.
right.
And Ceres is working its way through June, coming down this way below the Virgo star cluster in
that's
I don't see
Virgo.
the- Yeah, there it is.
I think
Virgo,
you mean
yeah.
galaxy cluster, Jerry.
Yeah. Yeah.
Well,
So
Chuck,
these are, go ahead.
Chuck, anytime you want to volunteer occulting reports, but Ceres being, I guess, the only small planet, dwarf planet in the asteroid belt, probably occults stars a lot, doesn't it? Goes across the
I
sky.
haven't seen a lot of them that come over our area recently. And you
Well,
wouldn't be
a
getting
rock
much
that-
information from that. That's a really well-known asteroid. I mean, it would be fun to do, and it would be a longer occultation, but it doesn't provide a lot of information because the orbit's pretty well resolved.
It's
Well,
about,
that's why spacecraft take pictures of it.
isn't it 300 or 400 miles across diameter?
I think
600
it's,
kilometers, I think.
yeah,
Well, kilometers, so, but it's still a sphere. And
Yeah.
big.
It's spherical.
I think
Not
it's
as big
actually
as our
600
moon?
miles. It's pretty good size.
Is our moon bigger?
No.
It's
Oh,
bigger
yes.
than-
I mean, our moon is bigger than Ceres.
Right.
Right.
What is our moon? About 3,000 miles across or 2,000?
2,160.
Okay.
And yet we don't have a dwarf planet orbiting us. We have a moon orbiting us.
Well, because it's not orbiting the sun. Yeah.
I
it's orbiting
understand that.
us.
Yeah,
If the Earth weren't here, then the moon would be a dwarf planet.
Moons have been in the news lately. Enceladus, which they either mispronounce or were mispronouncing. They're calling it Enceladus. I believe they've been calling what the ice planet, the ice moon of, is it Jupiter?
Saturn.
Yeah.
Saturn.
Saturn.
That we're not going to visit it as we are. Who are we visiting? Europa or
We're
Titan?
visiting everything.
I
We're
know.
about to even launch something, a lander to Venus, an orbiter and a lander
That's true. Boy, we're out there, aren't we?
coming up. I think it's called the Da Vinci probe.
Okay. But then Enceladus, they think, has all the stuff that you need for life, even though it's a big ice
Yeah.
ball with an underwater one. Okay.
The recent popular press claimed that it has all the ingredients for a what is it, a juicy burrito.
Phosphorus was added. Uh-oh, gotta
Yeah.
check the oven again. All right. Fantastic. Anything special about solstice involving the sky as far as we have a place where the sun goes right through the gap that, the ancients used to make sure on the solstice day that it would flood the tomb. You know what I'm talking about?
Yes, there's a summer solstice on apparently in Manhattan sometimes.
Oh,
The
that's
sun lines
right.
up right down one main street or something. And I
Somebody-
guarantee you that was purely by accident.
I believe somebody told me the Chumash word Anapamu has something to do with maybe solstice or a vantage point or vintage point up on the Riviera or something. I haven't looked into it, but that's,
Yeah, I don't know.
don't know. Okay.
So anyway, this is the constellation of Ursa Major, also the Big Dipper. In this picture, it's spilling its load here. But this might not be the way it's oriented in the sky right now. Sometimes I lose that when I do the planetarium. I adjust the framing. But the second star in the handle up here, Mizor and Alcor, are a nice visual binary. So it's a test of your vision. If you can tell these are two stars.
And
And
actually, the names Mizar and Alcor, Mizar comes from an Arabic phrase for the puzzle or the test, and Alcor means the answer.
Okay.
Huh.
So this is a nice photograph of the two, but this is a visual test for acuity and eyesight. It's not that hard. Most people can see it.
And if you blew it up a little more, Mizar would be a double there.
Yes.
They're both doubles, aren't they?
Yeah, they are, but spectroscopic for Alcor. And that extra little bright star that's not quite on a line with them, just above Alcor in this image, that one's called Sidus Ludovicianum because there was an astronomer in Bavaria about the time of King Ludwig, and he heard about Herschel and other people, naming stars and planets, Sinus Georgium initially for Uranus after the kings and stuff. So he said, I found a planet by Mizar and Alcor and I named it after King Ludwig. So it's
Is that this
Sidus
star here?
Ludovicianum.
Yeah.
And
yeah,
then
it's great.
he was hoping for some pension, and the
Oh,
king consulted
Yeah.
other astronomers and they said it's not a planet, so he
Yeah.
didn't get his pension.
not a planet, right?
No, I mean, if you say Cetus in Latin, it means a star.
Yeah.
And the genitive is Ceteris. Sidereal comes from that.
My understanding is more than half the stars in the sky are binaries, but very few of them like this, we can actually see them apart.
That's true.
Then how do we know the rest of them that are binaries? Can you just see fluctuations in the light? Is that what it is?
Yes.
Mm-hmm.
But that doesn't make them a variable star. That just means two of them are going around each other.
Yeah, it depending on how close they are and their relative sizes and brightnesses, it may cause variability.
Okay.
Like Algol is that way. It's an eclipsing binary system.
How
But
many
they've got to be in line
AUs?
with the Earth for them to see us. There's a whole lot of stars out there. They're just not in the right quite place to do an occultation for us.
Well, these two are about how many AUs apart? Or light something or other, light months and light.
Don't know that distance. I know it looks like it's 11.8 minutes apart.
Okay, that's
Didn't record how far apart they are in actual space.
how many minutes in a degree? 60?
60.
Okay,
And there's 60 seconds in a minute.
yeah, okay, arc seconds, they're arc minutes, right? You got-
Yep.
Right.
Right. There's Zwicky. SN Zwicky and his orchestra now playing at the Granada.
Yes. This is the host galaxy. And so it extends farther out here. This is a blow up of this picture. And this picture is a blow up of this picture.
And
So-
this is the one when we had to talk by the fellow about hunting for trying to distinguish the characteristics of dark matter and dark energy. This is that repeating supernova, basically, that he was talking about. I believe.
Yes, that's right. And so then what you're looking in real close here, this is with the Keck telescope. It's a near IR band. And this is the host galaxy, which obviously extends farther out here. And there's a supernova in this host galaxy, and there's a lens galaxy, which means there's another galaxy in front of it that is bending the light toward us. And light that goes around here comes to see us and looks like it's up here. These are all actually 4 images of the same supernova that you don't see the original of. And they show up at different times because the path length is different and they all travel at the same speed, the speed of light.
But why wouldn't it be a circle?
There's
It's
not
not
the
exactly
mass
central.
What?
It has to be exactly centrally placed for it to be a circle.
right.
Called an Einstein ring.
Yeah, right. So we get 4 blips. Why not 5? Why not 10? Why not?
The mass distribution in the lens galaxy determines the pattern, what you'd call the point spread function, or here the points spread function.
Yeah.
So it's just a low quality lens. You know, they didn't design galaxies to be lenses. It's just sort of an accidental pickup.
And why
It's
did
kind
they?
of like the very early lenses like Galileo used. They didn't know how to make a good lens. They didn't know how to test it. They just grind everything roughly spherical, polish it, and then they'd pick them up and test them and see if any of them worked. And if they did, they frequently stop them down, that is, blacken out the edge, because it's usually the edge that goes wrong. And if they didn't get too far down toward a pinhole, every lens will work as a pinhole. So
Herschel used to make his really high magnification lenses by just dropping molten glass into water.
right, get short focal length lenses there.
And then harden just at the right shape.
Yes. Now this is a picture of the central star in Cygnus, Saturn. And this is the Crescent Nebula up here. It's a very rich region of the Milky Way. There's a lot of gas up here. And this is a picture of that gas. The stars are de-emphasized. This is taken through a very narrow band filter. So it's just the hydrogen alpha lines. You can take this picture from lightly polluted areas and get good results because it filters, you're just looking at hydrogen alpha, and there's not a lot of hydrogen alpha lines floating around down here to pollute. The theme of this talk today, or this hour, is narrow band filters, looking at different bands of the IR. And this is an example of what you see when you look through a narrow band filter. This was taken by an amateur, and this is a fairly big swath of sky. So this is a camera with a short focal length lens on it.
Huh. What does hydrogen alpha mean?
It's the most prominent line at 600 nanometers that we see in the visible spectrum for hydrogen. Hydrogen alpha means it's the brightest line in that band.
It is red.
Yeah, it's red.
Has nothing to do with the type of hydrogen, heavy hydrogen, or
No,
It has to do with the energy levels between 3 and 2 that it's dropping down to emit the light.
well, is there beta hydrogen and gamma
Yep.
hydrogen?
Yes.
There are. Oh. Okay.
But that's not a characteristic of the hydrogen. That's a characteristic of the light.
Oh,
Right.
okay.
yeah.
Right.
The level jumping for the electrons.
So we're looking at a star nursery here.
Mm-hmm.
Yes, well,
Yeah.
we'll get to that.
Except that Crescent Nebula down in the lower right, that's a Wolf-Rayet star, I believe.
Yes, and this is stuff thrown off by that star.
Thrown off, but not a hypernova or
No,
supernova.
No,
Not that.
Nothing like that.
on the way though.
Is this re-looking at Hubble's deep field with Webb?
This is a relook at the Hubble Extreme Deep Field. See down here, Hubble Extreme Deep Field. And this is looking with the Jimmy Webb near IR cam
He was
and
a poser.
mid IR cam.
You knew him, didn't you, Jerry? You and Jimmy used to go out partying.
Yeah, Jimmy's my brother. Jimmy's my brother. So this is a apparently blank spot in Hubble, but it shows a galaxy, a very early galaxy with a redshift of 7.28. This is another apparently empty spot with another galaxy of 7.24. Now, these are back within the first billion years of the universe.
Yeah.
So these are very old, very, yeah.
Very early galaxies.
Yes, yes,
Yeah.
good. I got twisted up with old, late, and early. So, and these are, oops, too far. So these are the ages of our universe. This is apparently where the Big Bang came in, which is fully ionized. And that means up here, everything is just particles. There's a proton, there might even be just quarks before that, but there's electrons and neutrons and protons, probably just electrons and protons up here. And that all of a sudden the universe cooled down a bit, and they got what they call recombination, which is where the protons and the electrons combine. So it's not ionized. But there's no heat at this time. There's no stars. There's not no heat. There's heat, but there's no stars. So there's no. It's called the dark age, because nothing is exciting the hydrogen. But then in this period, the first galaxies form. The first stars form because of gravitational attraction between the hydrogen, and it forms large lumps of hydrogen, and then nuclear fusion starts. And then that's called the period of renormalization or reionization. So after the dark age, it's not listed here, but there's a period of reionization. Oh no, here it is, fully ionized. So this is reionization here. Now that you have fusion and the energy is being released, and it's exciting all the other hydrogen around there. So it's starting to make stars, and these are when formation of first astronomical objects in this period. And then it becomes what we know as the universe today. This
And when it was not ionized, it was opaque.
Yes, that's why it's called the dark ages.
Yeah. So we can't see that.
That's right. But what we're seeing now with James Webb, we're seeing things in this reionization phase. We're seeing things with the first stars, the first generation of stars, which is called population 2 stars, I think.
Population 3 is the very,
Three,
very.
I think
That's
three.
right. They added through. When I was young, it was population 2, but now it's population 3.
That's a
Okay.
long time ago.
It was. Matter of fact, I was born right about, yeah.
Well, back then, would it be fair to say that all your clouds were pretty much gas and not dust, assuming dust is pre-made stuff in
Yes,
stars?
back
Yeah.
in the dark age, it was all hydrogen atoms. There was nothing else, no
Oh,
nickel, iron.
There was helium.
Right.
Yeah, well,
And-
it's a little helium and a teeny little bit of lithium and stuff, I guess.
Yeah, and Ron,
Uranium.
I was gonna say to Ron, take a look at the axis there, the redshift axis is logarithmic. And then Jerry was just showing us some very, very distant galaxies that were redshift 7 and change. So they're actually to the right. They're actually to the right of that.
Yeah.
Okay, but
So this, and you notice the redshift can go up to over 1,000 back here.
Good luck.
Yeah.
well, here's the dumb question of the hour. I realize I asked nothing but dumb questions, but of all those small particles, would you think that the universe provides us a fairly equal amount of, is it about the same number of protons as electrons? And then later, I guess neutrons are made when they get together, but there wouldn't be an overabundance of protons and very few electrons, or the other way around, right? It's the quarks.
I don't know the answer to that. That's a very complicated question. It sounds like it's up there with the amount of matter and antimatter. I
Well,
do recall an estimated number of the number of electrons there are in the universe. Would anyone care to take a guess at it?
10 to the 80th.
Close? 10 to the 73 is the number I was told.
Oh, okay, okay.
Okay, electrons are matter, light waves are not, or light photons aren't.
Light
that's all.
waves are matter too. Energy is matter.
Okay. And there's no kin to, all right,
Now,
keep us on the tour here, Mr. President. I love
now
this.
we're shifting our focus, no pun intended, to the large Magellanic Cloud, which is what is it, a midget galaxy, dwarf galaxy, orbiting the Milky Way.
One of our slave galaxies, yeah.
Whatever.
Yeah.
So this is these are polarization studies, polarized light, and that's why we have some of the equations coming up. But this
Wow.
is a central region in the Tarantula Nebula, which is a nebula in the Large Magellanic Cloud. And the way the cloud is shaped and formed, you can estimate from our theories how much star formation is going on. And there's a lot more star formation going on than is predicted. So they're trying to figure out why that is. And it turns out the bottom line is, I'll jump right to it, is that not only is gravity holding things together, but as a result of this and other studies, magnetic fields play a role in holding things together and keeping the stuff bunched up so it forms more stars. Otherwise, it would just drift away more. This is a picture of polarized light, how the light is polarized from that emission in these clouds.
Wow.
And the polarization is a very interesting thing. You can, you wear polarized lenses on your eyeglasses, and it really does take out the glare off of the road. And if you look out at the ocean, it takes the glare off the ocean, because reflected light is very highly polarized normally. And the reason it's polarized is because the light that's emitted is not polarized, but on reflection, it becomes polarized because it has to, light waves make electrons oscillate back and forth as they contact that electron. And if the electron is constrained in one way, it can't move in one way, but it can in the other. Then when it re-emits the light, it only re-emits the light that's polarized that way. So that's how light gets polarized. The way electrons are constrained to move, to interact with light, to make polarization is through magnetic field lines. So
Of the four forces, that's the strongest, isn't it?
say what?
Of the four forces that we've nailed down in nature, the strongest is magnetism, isn't it?
No,
The strongest is the strong force.
yeah, strong nuclear.
Oh,
And
well,
then-
that's
and
very
then the
down in
weak
the atom.
force.
All right.
And then the electromagnetic force, and that's what we're talking about here, electromagnetics. And then gravity is by far the weakest. So this shows the Large Magellanic Cloud, and this shows that region of star formation in the cloud. And this shows a very close-up of the very hot stars that are being produced.
Huh.
This is a JWST image
Yeah.
of the Tarantula Nebula, and the region of starburst formation is this cluster in here, and all these gases. These gases should be, the stars that were produced here produce a very strong solar wind or stellar wind, and it would blow this dust away normally, this gas and dust, but something is holding it and keeping it from responding as much as it would to the solar wind. This is a Sophia. Yeah,
Well, in the world, they keep that thing still at 600 miles. an
they
hour.
don't. They just keep the telescopes pointed the same way. So this
Really?
is Sophia in flight. This was Sophia was retired in September 2012, but this is data taken before they retired.
2022.
What's that?
2022, it says.
Yeah. So Sophia, this is the purpose of this, is to look in the infrared. And a lot of the infrared is absorbed by our atmosphere and the water bands. So they try and fly above dry areas, but as high as they can get. And this, until JWST went up, which has completely replaced SOFIA with much more capability, this was the way you get far infrared imaging. This
And that was a
shows,
second generation one in the 747. There was a previous
Right,
generation with a scope in a C-141.
right.
yeah.
They would fly out of NASA Ames and Mountain View. Used to see those. I was going to mention one more thing, Jerry. So a friend of mine, Jane Houston Jones, I used to do workshops with. She actually went up in Sophia to count meteors. Okay, so that actually served as a meteor counting facility.
Okay.
Yeah, pretty interesting. So it had
Julian,
a lot of jobs, you know.
Julian
Yeah.
Knott, our late balloon fellow,
Mhm.
also went up on one of those meteor counting trips, but in a Learjet, I believe it was.
I see. Okay.
Can we assume that square hole they're looking out of is covered by glass or something?
No.
No,
Don't-
glass stops IR.
That's right.
Kidding. How,
Yeah, wide open.
what keeps them from
See
being
it.
swept out? Those suckers.
Everybody's got their warmies on. No, it's it's a robotic telescope. Nobody's in that same compartment.
Oh,
Yeah, and
You can see a 45-degree front surface mirror in there. That's part of their tracking system.
And that's a sealed off compartment, Ron. It's not like the entire interior is being exposed to the sky there.
okay. And it's got a balancing system that keeps it steady, even as turbulence would totally screw things up. You know,
It's got a
it's got a
gyroscopic
really-
system in there, yeah.
Yeah, it's got a really good gyro.
great. I wonder what that vessel is doing now. They're going to mount it on a pole and it'll be somewhere in a.
Hopefully it goes to some museum.
Yeah.
It's kind of expensive to operate.
Yeah.
And it just
Yes.
uses helium to cool the detectors down up there. So, and that stuff costs as much as good Napoleon brandy. That's what they told us in graduate school because we used a lot of helium.
But if our atmosphere keeps away the infrared, does that have anything to do with why the sky is blue?
No, the sky scatters blue light.
Yeah.
But it doesn't take it.
It's
doesn't
sort of
keep it.
similar. I mean, instead of scattering, the atmosphere absorbs the IR.
Well, we do see things in the red part of the spectrum.
It depends on the IR band, Ron. It's not the entire, red.
I got you.
Like there's a band around 6 microns that's they're called the water band, and that absorbs a lot of stuff. When they want a radar that is going to be very short range, so that somebody further away can't see it, they use 6 gigahertz for the transmission band. That band, which is the water band.
So the Webb made this thing, Sophia, obsolete.
Yes, the James Webb has superseded this. So it'll probably go to a museum. It's useful, but it's limited compared to James Webb. This is a Sophia image in the infrared of the region called, marked with a star, 30 Doradus. And that's the region that we're looking at.
And that is the Tarantula Nebula.
Yeah, this is, and I don't see 8 legs. If at best, I would call it the Crab Nebula.
Yeah.
That name is already used by something that doesn't look like a crab. So
So we're looking inside
Okay.
another galaxy, a dwarf galaxy that's orbiting us, part of the local group. We can see it that much. Do these little galaxies that orbit in the local group all have their own little black, I say little, their own monster black hole in the center like our galaxy and most galaxies, do you suppose?
For the dwarf galaxies, not necessarily.
Really?
yeah, these are not spiral galaxies and they do not have a central bulge. And the central bulge is usually the indicator of a very massive black hole.
But now our solar system is in one edge of our galaxy, so I'm assuming that this small galaxy or cloud, large Magellanic Cloud, is just outside our arm. If it were on the other side of where we are, we couldn't see it, could we?
Well, it's not in the same plane as the arm, so you're looking up out of the arm to see it.
Yeah, I understand that, but there may be little galaxies orbiting we can't see, wouldn't you think, on the other side of our
Oh, yeah,
galaxy?
they're discovering them all the time.
Oh,
Once you got infrared, you can start looking through that stuff and you can discover them. So
otherwise there's about a dozen little, there's a small Magellanic Cloud too, isn't there?
Yep.
yes,
Oh, yeah.
And they have names for all of them.
well, or numbers.
Triangulinium? No, what's the name of that one that sounds like a piece of mathematics?
Triangulum, but that's not a dwarf galaxy.
Well,
No,
that's not. What is it?
It's a galaxy like
Yeah.
ours.
Yeah,
Oh,
big and
quite
like
as large.
ours.
Not one of the little ones. Okay. Fascinating stuff, gentlemen. Look at this. Can't wait till we get to those those equations. Oh, here
Yeah,
it is.
we're not going to dive in very deeply. This is the Lorentz force, and it describes in classical electromagnetic theory, not relativistic and not quantum, the force on a particle, like an electron, is the charge on the electron here times the electric field. Now, these darkened things, the F, E, nu, and B are vectors. So they are not a simple number. And so this is a vector equation. The force on an electron due to the electric field is in the same direction as the electric field. Of course, because Q for an electron is negative, then the force is opposite the electric field. It goes the other way. But it still goes in the same plane as the field. The magnetic field operates differently, and that's indicated by this symbol here for the multiplication, the X, where you use this for everything in arithmetic and algebra. This is a vector product here called the cross product. And so you have the velocity of the electron, the way it's moving, and you have the B field, the magnetic field, and they interact by causing the electron's force to be perpendicular to the field, to the B field. And that's what this cross product means. And the way you figure that out is through what's called the right-hand rule. And so everybody's got to make this with your hands now.
Looks like one of your cartoons.
Yeah. So anyway, the IL, the I is the flow of electron, that's the current, and L is the unit vector for this direction. So because it's negative, the current will flow in this direction, the actual particle, the electron will flow in this direction. But this is the B field here down here. So that an electron traveling this way, perpendicular to the magnetic field here, so this is a 90-degree angle, will feel a force that goes this way. The force doesn't speed up or slow down in this direction where the B field is, but the magnetic field makes it go in a perpendicular direction. So this is how you back through the polarization to get to the electron motion and derive the B field, because the polarization is an indication of how that electron can move. So the polarization is along this direction, and we can see these things move this way. So you can figure out what the magnetic field is, and so you can generate the magnetic field lines for that. And so these are graphs. This is actually, these are graphs of the magnetic field line, the polarization in these things. And from that, they developed the B field lines. And the force in a strong magnetic field, you can get all sorts of twisted shapes. We make instruments based on the cross product of magnetic field with charged particles called mass spectrometers. So that's how you get the B field out of this.
Jerry, what was the problem that had surfaced this guy Lorentz solved when he came up with this? I don't understand what the
Well, the Lorentz force is a cumulative thing from the 19th century in classical electrodynamics. They were just studying electrons, how electrons moved in the laboratory. They made vacuum tubes with no air in it. And they would inject electrons into it in a magnetic field, and they'd see that the electron would take a circular path in the magnetic field.
Oh,
So they were just studying the motion of electrons and charged particles to generate those equations. And that was the sum of magnetic forces and electrostatic forces in classical physics.
And Jerry, if I might just say that it's the foundation of the cloud chamber too.
Yeah.
Oh, yeah. Magnetic fields are used to sweep the electron beam across the face of a television tube.
really?
A
Oh, yeah.
CRT, yeah.
CRT, cathode ray tube.
Yeah,
Huh.
electrons were originally called cathode rays. They didn't know what they were.
Right, yeah, I forgot about that. Well,
Thompson.
CRT, right?
CRT,
Cathode ray tube.
Yeah, cathode ray tube.
right?
That's how you focus these things, how you
Hmm.
aim the beam. Well, you do it by
Focus
high
coil.
voltage plates. It's more the EQ part of the Lorentz force.
Well, there are three coils on a TV tube, two of which do deflection, and the focus coil causes the electron beam to spin on its own axis. So it wants to stay together.
Well, is this part of quantum? The quantum guys
No,
coming
this
on?
is pre-quantum.
Yeah, it's classical stuff.
Yeah, it's classical.
Oh, okay, quantum mechanics.
So this picture is the sum total of Chandra and JWST images.
Wow.
It's false color. The purple and royal blue show where stellar winds from massive stars have superheated some of the gas. So and this is the net result of things that through this work, you see the interaction of these clouds determined not just by gravity and the stellar winds colliding them, but also by the magnetic fields. And magnetic fields are generated by moving particles. And the magnetic fields also influence the motion of particles.
Of charged particles.
Charged particles, yes.
And you can see the Webb contribution from the diffraction spikes.
Yeah.
Oh, yeah, yes, the 6.
And occasionally you get a object out there, a stellar object that's a nightmare. That's all magnetism. They call them magnetars. Are those common or?
It's not
Those are
all
extreme.
magnetism.
Yeah, those are extreme magnetic fields.
Yes.
They're so extreme that atoms are no longer spherical. They're like spindles. They're so distorted by the magnetic field. This is much weaker stuff. This is very faint. Nothing. The Earth's magnetic field is about 1 Gauss. These
Half a
are
Gauss.
fractions. What's that?
It's about a half a Gauss.
Well,
About a-
that's on the order of 1 Gauss.
Okay.
So this stuff is much weaker than that. But over these vast distances and competing with radiation pressure and gravity, it's a contender. And
Yeah.
it can't be ignored to calculate some of these shapes. So this was a good laboratory exercise to demonstrate that.
And Jerry, I was just going to mention, when I was at Arizona, definition of an astronomer is an order of magnitude specialist.
Right.
Very good.
And in this picture, you can sort of, it doesn't look like a tarantula, but there's kind of a black widow dropping out of the bottom there.
Oh, yeah, yeah, how about that? But it's only got 4 legs.
Yeah.
I used
I
to
don't see that at all. I
Right
see a
down around
scorpion. I see a scorpion here.
Yeah, going upward.
Yeah.
virtually all planets, all stars, all things have magnetic fields that sometimes change, like our North Pole is going to
Only
switch.
if there are moving charges involved.
Right.
Yes. And that is going to lead us into the Drake equation.
Ah, here comes the one we're gonna have fun with. Drake, what a guy.
Yeah.
He was into the mushrooms, wasn't he? Okay.
No, actually, this is pretty rational, I think.
Yeah.
He was not trying to predict the life. He was trying to get discussions of what was involved going. So the capital N out here is the number of civilizations in the Milky Way galaxy with communications, with which communications might be possible. R star is the average rate of star formation in our galaxy. That's a number that we can determine, not to within a high degree of accuracy, but enough that it doesn't. We don't need to dwell on it.
Right.
The fraction of those stars that have planets, we're coming up now to the fact that virtually every star seems to have some planets. The trick is the average number of planets that can potentially support life per star that has planets. But this was interpreted early on as just being in the Goldilocks zone, liquid water, and it can support life. This is not advanced life. But now we're getting indications that the Earth is very unique, and there's a lot of factors in this average number of planets that can support life potentially. It has to be a planet that was the result of a planetary collision, which gives us a thin crust, gives us a rotation that spawns magnetic fields because we have an internal dynamo. And we have a thin crust in addition, which gives us plate tectonics and exchange of gases and materials with the interior of the planet. We have other examples of planets, Mars, that has a thick crust and does not have a dynamo. It does not have a magnetic field. And so it's, even though it had water for a while, it's not something that can support life or primitive life as we know of now.
Well, I would disagree with that definition, because we're looking at Enceladus as a potential place that could support life. Mars could support life beneath the crust in the form of the bacteria like we have that live in rocks.
Right.
So I don't think it's quite that restrictive. But to have sort of the complex intelligent life, which is kind of handled by some of these other terms in the equation,
Right.
then you might need those other factors.
Yeah,
Right.
good point.
Chuck, I think the sink or swim number is capital L.
Yeah.
Well, let's the fraction of planets that could support life that actually developed life at some point, I think that's pretty much one for places like the Earth and Mars and possibly Venus. The fraction of planets where life that actually go on to develop intelligent life, I think that life that forms on Enceladus and stuff nowadays, they're going to have a problem even seeing that they're on what their environment is. And they may develop some kind of intelligent life like dolphins develop an intelligent life, but I don't think they're going to meet the next one of developing a technology that releases signals into space. But yes, this one is less restrictive than I may have implied, but those restrictions apply down to these other lines.
Yeah.
So,
and then that big L is where we're trying to really erase ourselves from the equation.
That's
right.
right.
This is the one that causes us our modern angst. Will we or won't we?
Yeah, I call it sink or swim.
Is that the L is the one that was added? Didn't they add another element to this equation recently?
No, I think this is pretty much it. The key to L is where you develop enough knowledge, but not with corresponding wisdom, so that you destroy yourself by nuking yourself and everybody else.
Right. Yeah. And Frank really put this together in the 60s, this equation, when Carl Sagan was 26 years old.
Well, not only distance prevents us from, seeing each other or getting in touch with, but time is probably even a bigger element. The time.
Well, that's in the end where it talks about current past light cone.
Current past what? Light cone?
Light cone.
And it's going to mention Ron, if you could find maybe a YouTube by Tim Ferriss, where he talks about this equation and everything. It's really brilliant. It's really neat. It's kind of old now. I think I first saw this in the, around 2000, 2002, something like that. But Tim Ferriss had this one two-part thing called Life Beyond Earth, I believe. Right, Chuck? Life Beyond Earth?
I haven't seen it.
Oh, it's phenomenal. And there was a book, but to see this, I mean, there's a real cute scene where he's talking about the Fermi question, if there are other civilizations out there, why don't they get in touch with us? So he sits down and sets up a table where he's going to have a crab dinner. He just sits there and waits for somebody to show up. It's really neat.
But is this
Nobody
equation-
shows up.
Is this Drake equation just a symbolic thing, or is it a actual piece of mathematics? Could we insert numbers for all those letters?
Yeah,
That's
that's
what
the
you do to get an
intention.
idea.
Yeah. You know, again, these numbers can float. They can really float, like you've been listening to. So
Have you ever seen somebody, have they zeroed in on a bunch of exoplanets, a solar system, and put in an 8 here and a 2.5 here? And
No,
well, you know, so Ron, you can see that, you know, since Kepler has come up with over 5,000, you know, extrasolar planets, this equation is going to have different fits, right? It's going to have different feed-ins. So the equation is firm, but the ingredients are changing. They're always
yeah,
changing.
this is more like a recipe
Yes.
than anything else. And that F sub P, fraction of stars that have planets, I mean, we used to think that was a really, really tiny number.
Yeah.
It turns out it's not. It's a big number, you know.
Right,
So our interpretation of what this tells us has changed, and now it looks like life
that's
is a lot
right.
more probable.
Well,
Then you've got that L that we're trying to prove that oh well, it doesn't matter in the end.
Right.
Let me make a
It's like
comment here.
Chuck, you're making a pizza and you're changing the ingredients.
go ahead, Jerry.
It says which are on the current past light cone. That
Mhm.
means that we can see them.
Yes.
So it takes time for a signal from one of these civilizations to get to us. So if they exist a galaxy away right now, we would never see them because they're not
That's
on our light cone. So
Yeah.
these have to have been, if they're farther away, they have to have been longer ago.
Oh,
Right.
And
Yeah.
also, you know, that current light cone now, if the L is short, it doesn't matter.
Right. And Tim Ferriss points this out about civilizations coming and going by just showing you a movie of a Christmas tree with twinkling lights on and off and on and off. And if they're on at
Yeah.
the same time, then those civilizations could talk to one another. But if they're not, they can't. You know, that's the idea.
I think there's a much more complicated formula of maintaining two-way conversations here.
Yeah.
Well, if it's going to take 500,000 years for their signal to get to you, it's going to be the same amount of time for our signal to get to them.
That's right.
Forget
That's
it.
why these
Yeah.
flashing Christmas tree lights have to coordinate.
That's
Yeah.
right. That's right. That Tim Ferriss points it out in Life
Yeah.
Beyond. It's really good. It's really good. Recommend watching it.
well, given the fact that we've been sending radio waves and television signals, for example, for 100 years now, we've
Mhm,
gone way. Could they get those on a Alpha Centauri? I know it's
Yeah.
only 4 now.
Sure.
Could they? They could
Yeah,
take
I
that-
Love Lucy is about, you
Right.
know, 50 light years out there, 60
Yeah.
light years out there.
Alpha
Yeah.
Centauri thinks that Trump is still president.
Yeah.
But the other thing that creates the problem is that radio waves are spherically spreading. They diminish by 1 over the radius squared. So, you know, like with our spacecraft, the Voyagers, which are way out there, in order to get that signal back to Earth now, they have to slow the data rate way, way, way down, like 100 bits per second. Because if it was faster than that, we couldn't receive it. It would be buried in noise.
Yeah.
Yeah.
Principle. Advanced civilization would know how to do these things, right?
Yeah.
Wait, you don't get to vote on the laws of physics.
You don't get what?
You don't get to vote on the laws of physics.
Oh,
Yeah, but you can use a very directional laser beam with really high speed modulation to get over the data rate and the spreading problem.
Right. And that's kind of
Right.
how.
But then you'd have to point it, you'd have to know where we are and point it toward us.
Yes.
Yeah.
well,
Said-
I've heard that there's other ways that they could conceivably communicate and using light itself to fluctuate.
Yes.
Right.
That's
what
all
I do.
radio is, Ron.
Right.
Well, I mean, if we saw a star beaming, you know, a certain, not just a variable, you know, on a regular basis, but communicate. If we found one, there'd probably be intelligent life around it, wouldn't you think?
That's the whole idea. You look for signals that are not characteristic of noise.
And that
Right.
wouldn't be radio. Okay, fascinating stuff.
Yeah.
Good
In-
old
in a-
Drake.
In a real way, I was going to say SETI has kind of like changed into METI, message, you know, M for message instead of search for. And so there's a lot of activity pointing to the fact that, how you send messages might enhance, the SETI part.
Or it might make it worse because actually
Right.
we're moving toward quicker transmissions and to avoid interference, we break them up into different frequencies and jump around and it starts to
Yeah,
look
they
more and
might
more
not
like
have
noise.
5G yet.
They might not have what?
5G yet.
Yeah.
They want to put a 5G transmit station locally, 2 blocks away from me. And I've been researching that. 5G puts out enough power that it causes fires in nearby foliage.
I would doubt that very
Yeah.
No,
seriously.
I found that in my, looking at some of the references.
Yeah.
That's why Verizon doesn't want to put their antenna in the middle of some eucalyptus trees.
Gentlemen, we've run out of time, but what a way to close. It's just fascinating. They may have to add an M to this this equation if they find something on a moon. But they're
Well,
hoping-
that's kind of under planet,
Yeah.
think so. Okay, well, but can you imagine growing up and living on a moon in intelligent life? Your whole world would be that planet you were orbiting. Heck,
Kind of like Pandora.
exactly. Gentlemen, you did me in again. I got to tell you, thank you. Take care of yourselves and enjoy. I guess this is Juneteenth, and
Yeah.
I'm amazed at how blurry I look. That's pretty much how I feel, Father.
It looks pretty good.
Thank you. I'm gonna get this fixed with our old friend Don Farley. Thank you for giving me his name yesterday, Jerry. And you got anything to close with? What are we doing out there with outreach in the next day or two or this week, Chuck?
Let's see, what do we have? We have Wednesday night is Carpinteria State Beach, Thursday is Bacara. Friday, what's Friday? Friday is Refugio. Saturday is Lopez Lake. Sunday is Trinity Episcopal Church, which Tom
Fantastic.
didn't manage to get on the webpage, but I'll send out an email to remind people of that.
And even though we have these other July sky, gray sky, August, it's really going to be nice from now on, isn't it? Where this is the viewing time of the year.
Let's hope.
June bloom. Well, let's get together.
August the foggiest, but I like Foggust better.
We get it, don't we? It's going to be a
Yeah.
hot summer. I got a feeling. Happy solstice.
Yeah.
Our friend Tessa Flanagan used to be in the solstice parade. She can't right now.
Yeah.
She's still recovering. Look for
Yeah.
her. Forward to her, and I'll see you guys on screen. I hope next
Okay.
Monday morning,
All right.
11 o'clock for the SBAU Astro Hour.
Bye.
Ron here and the rest of the gang. Thanks, Jared. Thanks.